All right. Hello and welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of nearly 100,000 computing professionals and students. My name is Michael Zeller. I'm the head of AI strategy and solutions at Temasek. I'm also an ACM member and serve as the treasurer on the executive committee of ACM's special interest group for knowledge discovery and data mining, SIG-KDD, the premier international organization for data science. To learn more about my background, please check out the bio window on your screen. For those who may be unfamiliar with ACM or what it has to offer, here is more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. ACM provides timely computing information published at ACM, including communications of the ACM and Q magazines, the access to the ACM Digital Library, which is the world's most comprehensive database of computing literature, international conferences that draw leading experts on a broad spectrum of computing topics, support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize in Computing Awards, and the updated ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in a professional practice. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Now, before we get started, I'd like to mention a few housekeeping items shown in the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you will find some additional widgets and resources. If you are experiencing problems with the slides or audio, press the F5 key in Windows, Command R if you're on a Mac, or refresh your browser on a mobile device. Or you can close and relaunch the presentation. To control volume, adjust the master volume on your computer. If you have questions during the talk, please type them in the Q&A box at any time and click the submit button. I will organize the questions as Anima speaks, and she will reserve time at the end of the presentation to address the questions. This session is being recorded and will be archived. You will receive an automated email notification when it becomes available, and check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey open on your screen. Please take a minute to fill it out and help us improve our tech talks. You may also open the link to the survey at any time from the resources window. You can use the Facebook and Twitter widgets at the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag ACMLearning. We will be watching for your tweets, and we also have a community discourse page to continue the discussion after this webcast, including questions we won't be able to get to in the Q&A session. Now, today's presentation is titled How to Create Generalizable AI by Anima Anandkumar. Anima Anandkumar is a Brand Professor at CALTECH and Director of Machine Learning Research at NVIDIA. She was previously a Principal Scientist at Amazon Web Services. She has received several honors, such as the Alfred P. Sloan Fellowship, NSF Career Award, Young Investigator Awards from DoD, and faculty fellowships from Microsoft, Google, Facebook, and Adobe. Anima is part of the World Economic Forum's expert network. She's passionate about designing principled AI algorithms and applying them in interdisciplinary applications. Her research is focused on unsupervised AI, optimization, and tensor methods. She is also an ACM member. Now, Anima, without further ado, the stage is all yours. Please take it away.
so happy to be here and talk to you about how to create generalizable AI, take deep learning to the next level, build a new foundation, and further make strong impacts in a number of domains. The last decade, it's been really exciting to be an AI researcher and look at all the impressive gains that deep learning has brought us. And for that, it's not just the algorithms, but also the data and compute infrastructure, the trinity together that has made this progress possible. The deep learning revolution started with the creation of ImageNet, and for the first time, there was a large collection of labeled images. And that's when we could train large neural networks to learn features from the data itself. And finally, the compute infrastructure, being the NVIDIA GPUs, was critical for this revolution, because without that, we couldn't process this large-scale data and train large-scale models. And the parallelism of GPUs was critical to be able to do this at a large scale. And that's why this trinity of data, algorithms, and compute infrastructure has been so crucial for this current AI revolution. And that has led to so many impressive gains. Some of the famous ones are the AlphaGo beating the human champion, the NVIDIA GANs generating photorealistic images that have passed the Turing test, meaning we can no longer tell if this is a real person or a fake person generated by a GAN. And so we are now at this stage where many of the tasks that were thought to be impossible for AI are now getting done. But at the same time, there is so much more room for further improvements. And in so many domains, AI has not lived up to its hype. For instance, autonomous driving is perhaps the most visible one. There was a lot of excitement over the last few years to be able to get autonomous driving onto the roads. But we've only seen some failures, and the safety criticality of it makes it extremely challenging to be deployed in the near term, because AI is not robust and not able to foresee all possible scenarios in the real world. Similarly, now with the coronavirus, we're all at home, we are doing these virtual meetings, and there is a clear need for AI to take over many of the tasks that were earlier done by humans, in particular content moderation and content understanding. And it turns out the AI is still not up to the job, right? AI still cannot understand the nuances in language, and especially if somebody's trying to circumvent and manipulate those systems, it's not able to overcome those challenges. And in particular, it's not able to reason and understand what it is that it's supposed to moderate. And that's why we still have a lot of failures with the current generation of AI. And so then the question is, what are these gaps in current forms of deep learning, and how do we fix them? And so what is this path to generalizable AI that can overcome these challenges? And for that, I'd like to start with trying to break down any AI algorithm, right? Because I'm an algorithms researcher, I'd like to understand what are these key ingredients and how do we fix gaps in each one of them. For instance, for me, an AI algorithm, first of all, has to take in data, right? So what is the kind of data it's going to work on? What is the quality of data? And then the second part are the priors. What else do we know about the domain? What kind of inductive biases can we build into our models? And then the last part is, what is it that we want to solve this for? What is the task at hand? And if this is an interactive algorithm, what actions can it take and interact with the environment, right? So this combination is what makes a design of an algorithm. And then the question is how to further improve what we have in our current deep learning systems. So typically, like the design of the kind of data we use and the priors we have is called learning, and the design of actions is usually called decision making, right? So there is some separation between the two, but in totality, that's what gives us an AI algorithm. So what do we see with the current deep learning methods? The most of the dominant methods are supervised, so they're extremely data hungry. They require massive data sets. Last year, ImageNet was in fact retired because it was considered to be too small, and now the models are overfitting to that. So we are now requiring more and more labeled data, and that's not within the reach of every company, and especially for academia. It's expensive to label this. And then the second aspect of priors, we are not building robust priors into our current deep learning models. In fact, they're so brittle that it's so easy to fool the current AI models. There are these famous examples where in an image you just put a few blocks of, here you see black and white blocks, and that's enough to change the decision or the inference of the algorithm, and that shows how brittle it is. This is not yet ready to be on the roads. And similarly, we don't have domain specificity. The promise of deep learning is this is universal, which is great, but if you don't further specialize it to the domain, we can't enhance the robustness, and that's why we need domain-specific priors. And lastly, with the design of the tasks, currently it's very simplistic. We have some fixed tasks, have overall accuracy of classification to be maximized. And but in many cases, that's not what we all need, right? In the real world, it's not just about one number or objective, but a whole set of different objectives. And the limitation is currently we can't incorporate that well. And the other limitation is we work only on limited benchmarks, especially as researchers. ImageNet is perhaps the most heavily used benchmark, but then it has severe limitations. So we have to be aware of that and try to design not only new fixed benchmarks, but benchmarks that can be an open world setup where we can keep growing the data in the benchmark itself. And this is crucial not just for performance, but also issues such as bias in our AI models. This bias starts with the data itself, these benchmarks having heavy bias against minorities. For instance, with face recognition, we know that it's celebrity data sets, and that's heavily biased against minorities. And the effect is these AI models then creating heavily biased results, and that could be used in sensitive applications like law enforcement. So there is this whole field of AI ethics that aims to tackle these issues, but I think to me at the core of it is that we are defining tasks in a very simplistic way. We are training them on biased benchmarks, and we need to fix this foundation. So given that these are the limitations, let's think about what is the next frontier in AI and how do we build better foundation for the next generation algorithms. So when we look at data, we have to do unsupervised learning, right? So the next revolution is going to be unsupervised learning, and it has already started. We need to be able to disentangle different factors of variations without being given that supervision. Because no matter what you label, there's always going to be other variations that you just cannot label, right? And unless an algorithm can understand that, it's not going to be able to work well, be robust, but also lots of data is just unlabeled. So for the scale in many applications, we need to have unsupervised methods. And we also need to have good domain adaptation methods that can go from one domain to another and transfer the knowledge seamlessly. In terms of priors, I think we need robust priors that make a big difference. And to me, the priors can also help online as the algorithm is making certain inference. For instance, if it wants to address whether a cat is in an image or not, it shouldn't be just one shot, right? There should almost be like a different feedback that says whether this is a correct answer or not. So we need this recurrent feedback, and I'll go into that in depth in this talk. We also need to infuse different kinds of domain knowledge. The question is, what is that right balance between the knowledge of the domain especially what domain experts can bring in, and what can black box methods like deep learning bring in, and how to blend that. And then the third aspect of robustness is compositionality. We didn't build an aircraft all from scratch, everything just jumbled together, right? But that's how we're building our large neural networks. The GPT-3 model, for instance, has 170 billion parameters, just right, all mixed up. We don't know what is the functionality of this block versus the other. We have a few intuitions, but it's still all entangled together. And all of engineering has taught us we should be modular. We should be able to compose different parts and still get the result in a guaranteed manner. And that's what I think we need to bring also into AI. So I'll talk about compositionality, which I think is very crucial. And then the last part of adaptivity, I think having not just one fixed benchmark and fixed task, having multiple tasks and domains, and ultimately being able to do online and continual learning. So you keep continuously learning like humans do, hopefully most humans do, and then only then now we can have algorithms that can go interact in the real world, have applications like robotics and autonomous driving. We really need adaptivity. So these are all aspects that I'm very excited about, and we have several works on each thread. But in this talk, I will focus a lot on robustness and talk about these three aspects: how to build recurrent feedback, how to incorporate domain knowledge, how to build in compositionality, and show some exciting results in these realms. So for the first aspect, I'm taking inspiration from the human brain. Right, and that's where collaboration with Doris Sau at CalTech, who is a neuroscientist, has been very important to understand how our brain works and what inspiration can we draw and build this into artificial networks. So if you look at the human brain, it's hierarchical, similar to artificial networks, right? As you go to the higher levels in the brain, you have increasingly complex features, from like simple lines ultimately to features like faces. So it's similar to what we see in artificial neural networks. But the difference is that the human brain isn't just a feed-forward network. It's a combination of feed-forward and feedback. So here we have these like feed-forward links. So from the external world, we have a feed-forward link, but then there's the internal model of the brain, and then it kind of goes back and forth, right? So that's why even if you see this image of a blurry cat, you can tell, I think this is a cat, right? So what's happening internally in the brain is it's trying to de-blur that and trying to infer that it is a cat. And for that, the critical aspect has been the internal model that we have of all objects. We have this prior of what a cat should look like, and we are trying to match to that prior. Or rather, we are trying to do posterior inference in the Bayesian language and inferring that cat is the most likely object because I'm trying to look at priors of all objects, and the cat is the one for which the posterior is maximized. And that's the Bayesian theory of the human brain. And if you believe this theory, we can ask, why not do the same with artificial networks, right? Why not have both a generative model and a predictive model together and use the generative model as a checker or a feedback before we make our inference on whether there is a cat or not, for instance. And for that, we need to bring these two frameworks, the classification and generation, together, right? The ability to classify whether an image has a cat or not, and the ability to generate a cat should be all built in the same model. And that's what we did with what we called a convolutional neural network with feedback. And it's also extensible to any other neural network architecture. The key is this feedback connection. And for that, I'm going to give a quick, simple intuition. If you look at logistic regression, that's the most popular and perhaps the simplest classification method. You can ask, what is the generative model, or what is the distribution on the input for which this would be the Bayesian inference, or this would be the posterior? And it turns out if the data is distributed as mixture of Gaussians, then the inference, right, reduces to logistic regression. And so that's where we can kind of try to reverse engineer what is a valid distribution given this classification rule of logistic regression, and then does it satisfy the Bayes rule. So we can ask the same question about neural networks. Given a certain neural network architecture, we can ask ourselves, what is the generative model for which the neural network is the inference rule, is the Bayesian inference rule? And we can try to reverse engineer, and hence we have a valid distribution. That may not be the true underlying distribution, but at least it's a valid one for which the Bayes rule is satisfied. And hence we have this consistency between the generative model and the classification model. And that's how we designed in an earlier work that the generative model that corresponds to a feed-forward neural network turns out to be a model that tries to reverse these connections. So in the feed-forward, you're going up the layers. In this generative model, you're trying to generate from the label to the input image or whatever intermediate features you stop at. And then to do that, it turns out that because we don't have invertibility, right? So in a neural network, typically we have loss of information. Max pooling loses information. If you reduce the size of your layers, you're losing information. And to overcome this, we need to design now latent variables that try to predict what is the best way to invert. And that's why here we not only have this reversal, but also latent variables. And this is also very intuitive because now we're building in unsupervised learning, which is, I think, the key for robustness. So we don't just have supervised learning of trying to fit the image to the label. We are also doing unsupervised learning of trying to infer these latent variables which capture the variations in the image. And that's needed to be able to generate the image from the label. And when we do this together, right, we can now do message passing in this Bayesian network. And that's how we get the feedback. And if you unroll this, what you now see is feedback connections, right? So there's the feed forward, and now from in the next iteration, you're doing the feedback and again feed forward. So you alternate between feed forward and feedback, and that's why we call this recurrent feedback. And the idea is to ensure self-consistency. If the classifier thinks there's a cat, we should be able to regenerate that cat in the feedback connections, right? And only if that consistency is there, we can tell for sure there is a cat. And if you do this over several iterations, hopefully we have a robust classification that it is a cat. And that is the whole idea. And that's where we can use this to handle all kinds of corruptions without ever having seen it during training data. The key difference here is all these, I guess, unfortunately, even the GIFs don't play here. I'm sorry, this is unfortunate. But I have several in these slides. That's really unfortunate. But yeah, if you can play the slides offline, you can tell that all the corrupted images, you can progressively denoise very effectively using these using the neural network. So which is good. Sorry about that. I really didn't know that nothing plays here. So, and it turns out that now with the feedback connections, we can dramatically improve the robustness. In particular, even the challenging case of adversarial robustness. So in a neural network, the standard one in blue, if you just train it in a standard way, and then you add some noisy samples, right? The epsilon is the level of noise. Very quickly, you degrade performance, right? It's almost zero here, the accuracy. Whereas now you see that the feedback network has inbuilt robustness. And that is crucial. The feedback is crucial to get us this robustness. And you can further enhance this robustness with adversarial training. And for the feedback network, it's crucial to add both clean and noisy images together, because it can try to denoise the noisy images into clean images, and through consistency rules, come up with the inference of what's in the image. And that's why if you see here, without the clean images, the performance of the feedback network is bad, but with also added both clean and noisy images, it's really good. And that's the idea, that we can incorporate both the knowledge of clean and noisy images and use feedback connections to enhance the robustness. So then the last aspect of it is, yes, we took inspiration from the human brain to have these feedback connections. Now we can ask, how biologically plausible is this? And can we try to do regression to the neuronal data, biological neuronal data? And it turns out this brain score is higher than the standard neural networks. And there are some limitations with the current neuronal data set, and we are working on even better ones. And we believe that this feedback network should have much higher biological plausibility compared to a standard neural network, because human brain has these feedback connections. So yeah, in conclusion on this aspect, the main theme is, don't just do feed-forward classification over many layers of a neural network. Add these feedback pathways that the human brain has, and build some generative model into this feedback, right? And by building this, you're now almost checking it back. If you think there is a cat, can I generate a cat back? And then I kind of go through several cycles of this, and through that, we have a much more robust inference. We can handle adversarial robustness and other kinds of corruption robustness, and we also have better biological plausibility. I think this will be very critical in so many domains where robustness is important. So now let me move to the next aspect, which is compositionality. Like I said earlier, it's so important to not just have one big monolithic network, but like modules where we can mix and match and come up with new settings which were never seen in training data. And for that, I believe that neurosymbolic systems are critical. So the main idea here is that there has been a long going debate between people who believe in symbols and people who believe in neural networks or connectionists, right? The idea is symbolic AI has a set of symbols, and then there are rules. You construct logic, you can do inference, right? That's why it has explainability. On the other hand, neural network is about training on any kind of data, right? But there's no explainability, and you can try to fit to whatever the training data is available. On the other hand, both these cannot extrapolate to entirely new scenarios that is not seen during training. And what we've shown is with neurosymbolic AI, you can overcome the shortcomings of both these aspects. You can now build in explainability, you can have generalization, but you can also have extrapolation to new examples because you can compose these different systems together. And let me show in detail what this means. So, we looked at this task of mathematical reasoning, right? Like we took about 25 functions like trigonometry, logarithm, basic mathematical functions, and numbers and symbols, and asked, can we have the method learn this on its own, right? So that it's not just given by fixed rules. We don't pre-program all this. It is something that is learned with the availability of data. And the data can come in terms of symbolic equations. It can come in terms of evaluations of functions numerically. and it can come in terms of numbers itself being encoded as decimal tree. And you can see these are all inherently compositional, right? So in this case, we know that these systems are compositional because we are composing different functions, numbers, and symbols, and coming up with the ultimate result. And so we thought this is a great test case for how we can build neurosymbolic AI. And to do this, we now want the neural aspect as well, meaning we are now learning continuous representations for symbols, numbers, and functions in a common embedding space, right? So the whole intuition is, 1 minus sine square of theta, we know is equal to cos square of theta, right? So the embedding of cos square of theta should be close to 1 minus sine square of theta, right? So this idea that now there is some embedding space where we can represent the relationship between different symbols, numbers, and functions is now crucial, because we can further compose these embeddings and come up with results for extrapolation. And we use TREE-LSTM models. We could use other models, with this kind of compositionality, because at each step in the tree, we can now have an embedding and an intermediate result, and we can reason how close this embedding is with respect to other embeddings, right? So that's where we can have this compositionality. And it turns out that it's not just generalization, but extrapolation to harder examples. We get very robust results because of this compositionality of TREE-LSTM compared to just baseline models that don't have compositionality. And it turns out that we can further enhance this extrapolation ability by building in external differentiable memory in terms of stack. And if you look at just the TREE-LSTM with higher depth, the performance drastically drops because it has never seen this during training, right? Whereas having the stack makes this much more robust in terms of being able to extrapolate to harder new examples. And by the way, if you use transformer models, which are very popular, right, they break down even when there is slight shift in distribution. And so for this setting, there would be a drastic drop in terms of accuracy, and that would come nowhere near this accuracy numbers we are showing here. And that's why it's important not just to build big models, monolithic one, and say that we've done our job. If we want to handle new scenarios that are not seen during training data, compositionality is a key. And we've shown that with the math reasoning task, but this is applicable in so many other settings. And being able to combine symbolic expressions with numerical data and having this ability to extrapolate to harder examples, I think are some key requirements for robust AI. And we've shown that compositionality can be incorporated through these mechanisms. Now I want to move to the role of priors, right? Because that is the other facet of robustness. We wanted to incorporate the right kind of priors or domain knowledge. And it turns out, especially for AI for science, this is critical. And at CalTech, I co-founded AI for Science initiative to bring the whole campus together in terms of how we can build AI into different scientific applications. And that's when I got to understand all the challenges in different domains and why it's not just straightforward to just apply a deep network into those domains. And for instance, the data is so limited in many scientific domains, right? So that's not enough. And we have so many other requirements of robustness, and that's why having priors is so critical. The priors can come in terms of structures such as graphs. Right? Graphs are so natural in so many settings, and I'll show you an example with molecules where we use graph neural networks. My work has focused a lot on tensors, which extends matrices to higher dimensions. And so to incorporate multidimensional data and higher order correlations, these have been great. We can also incorporate all kinds of laws of nature, whether it is quantum laws or Newton laws, right? In all these settings, we don't have to learn that from scratch. We can incorporate what we are sure is good knowledge. And we can also have simulations that are available in so many settings for us to generate data and not just rely on real data. So I think these are some great ways to incorporate priors. So at CalTech, I'm part of CAST, which is the Center for Autonomous Systems and Technology, and it has so many exciting robotic applications, whether it's the bipedal robot or the drone arena, and we have like a wind tunnel kind of facility where we can test the drone for different wind conditions. So these require highly robust AI, right? And that's where, if we are now trying to do prediction of the new state, given the current state, we want to not just learn an AI from scratch, but augment the current controllers or the current models. So there is usually a baseline model of how the state should evolve, and that's given by Newton's laws of motion. But some aspect is hard to model, and for that, we can use a neural network and learn from data. And it turns out for drones, the critical aspect to model is the aerodynamics, and that's really hard, right? So we can learn this from data, and once we've learned it, then we can bring it along in the loop. But there are some challenges here. If the neural network is not robust, the drone just crashes. And in fact, that's what happened when we just put a standard neural network in the loop. And then we were more thoughtful and asked, okay, how do we make the overall system, that uses the known model from the domain and the learned model from the neural network, overall it should be robust and safe. How do we build in these safety and stability guarantees? And how do we ensure it can generalize to higher speeds than with which it is trained for training data? And so we incorporated all these requirements in a thoughtful way, and then we've been successful in being able to not just land faster, but also satisfy all the safety and stability requirements. So let's see if the video can be played now.
In this work, we present the neural lander, provably stable drone landing control using learned dynamics. The neural lander improves upon the baseline controller by incorporating learned dynamics. As you can see, the neural lander is capable of smoothly landing in ground effect. 3D landing involves horizontal and vertical motion. Our method still performs well here. We learn residual dynamics and cancel them out in our controller.
So moving on, what that showed is it's possible to incorporate learning in a thoughtful way into control loops, but we have to be careful in terms of incorporating safety and stability requirements. As another example of using deep learning in chemistry, it turns out that if you do this from scratch, it's not going to generalize to different molecules. For instance, if you only train on simple molecules like water or hydrogen fluoride, and you want to generalize this property prediction to very big molecules like drug-like molecules, there is no way, right, for deep learning to directly generalize. But on the other hand, from quantum theory, there is something known as molecular orbitals. These are features that are cheap to extract, and they're very universal. So now we are given an embedding for the chemical space, so we don't have to force the neural network to learn it from scratch. And that is great for robustness and the ability to extrapolate to harder examples. So we build that with graph neural networks. Graphs are natural because molecules, are in terms of graphs. So building the two together means that what we call ORBNET has the best performance, right, in terms of R-square score. And also it's very quick, 1,000 times simulation speed up compared to methods like DFT, whereas the standard deep learning methods without these kind of domain-specific features are pretty poor in terms of the R-square. So that's why it's important to have the domain knowledge and build in deep learning. And you can also see that's why we can also work with much less data for training compared to other methods. And similarly, we also showed in the class of learning PDEs, which involves a lot of scientific applications, if you want to be independent of the resolution, Because, if you think about fluid dynamics or applications like that, right, you can't just remain in a fixed resolution. You want to look at the solution at various resolutions. And for that, we look at the structure of PDEs, and we want to learn the underlying operator itself, or the kernel, right? So that way, it's now generalizable to different resolutions, even though it's not seen it during training data. And we can also incorporate multi-resolution ideas, right, from classical methods and build graph neural networks with multiple levels. And putting these together means that we got it to work in any resolution without having seen training data in higher resolution, and do much better than just standard neural network or even some of the classical methods. And so that's why it's important to ask, what is it that we want from the domain, right? And what is it that black box methods like neural networks can build in, and put the two together in a very problem-specific way. It's not one size fits all. We have to be very thoughtful in terms of what works for this domain, what are the requirements for this domain, right? Do you require extreme robustness for this domain, or is there very limited label data in this domain? All these aspects we have to think about before we bring in machine learning into the domains. And that's where working with domain experts here at CalTech and elsewhere has been so eye-opening for me to understand this. Lastly, I want to just give a few quick snippets. I know we are coming to the end of the time here, but kind of show what aspects we can enhance in terms of unsupervised learning, and in terms of understanding the trustworthiness of these algorithms, and finally, can we design adaptive algorithms? I'll give very quick snippets, and then we'll end after this. So I think a very critical aspect is disentanglement learning, right? So we want to discover latent variables, but we also want them to be interpretable, and we want them to control separately. And what we did in this ICML paper that appeared recently was that to be able to have disentangled generation, for instance, I should be able to have image of different kinds with bangs, or have glasses on different people, right? Or have a person smiling. So the idea is being able to control all this independently, right? You don't want other things to change. If you're only changing bangs, you want the rest of the face to be the same. And the idea is, can we learn this automatically from data? It turns out it's extremely hard to do it in an unsupervised way. But even if you have a tiny amount of label data, that's already much better. And that's what we show with just as little as 0.5% of the label data, we can get very good results in terms of disentanglement and also realistic generation. So we can have both the ability to generate very good images, but have the control on what we generate, which is what is important. Another very popular framework now is self-supervised learning. Okay, you don't have supervised data, let's just create supervision, right? But the core idea there is that there's so many invariances in data. Can we now do data augmentation by generating these invariances, right? And then kind of ensure that all these invariances are incorporated into our training. For instance, simple things like rotation, crop, all this you can enforce that you should not change your label based on that. And that's a very popular mechanism now. The other is self-training. You can pretend that you have real labels, but the labels are generated from the model itself. And then you can retrain the model with this, right? So you're kind of using just a self-training loop. And so you ask, why should this work at all? I mean, there's no new knowledge being generated here. So the reason it works is because, right, it's trying to enhance the representation space because images that are similar in this space should have similar labels, right? So that's being enhanced if we ensure that pseudo labels that are high confidence are first used, and so you can further improve the confidence on the other images. So because it's important to select images with high confidence levels, as a curriculum in the self-training loop, we asked the question, can we design robust measures of confidence? So it turns out that standard neural networks are overconfident and not well calibrated, and can we now generate better ones? And we applied it for domain adaptation. So here, in the target domain, you can do self-training and you can try to learn and fine-tune your model with pseudo labels, but you want to only first train with high confidence labels. And what we proposed was an angular measure that's much more robust in terms of having a good confidence level, because it nicely captures the separation between the different categories. And it turns out to have much better performance in terms of self-training compared to standard measures, just like the softmax score in neural networks. And so it's important not just to think about training algorithms, but also to think about confidence measures, right? How do we have trustworthy AI that can give us the right confidence measures? So that was important as well. So, I talked briefly about in unsupervised learning having disentanglement and being able to design good confidence measures. The last aspect, I'll quickly give a snippet in terms of how we can have adaptive algorithms. Not just train on a fixed task, but be able to adapt online if there are new tasks. And, this is in the realm of meta reinforcement learning. Here, there's a set of tasks rather than one task, and the agent should be able to do all of them, right? So rather than playing AlphaGo with a fixed set of rules, what if it suddenly has to play chess, play some other game, and do that adaptively? And in this simple toy example here, this bot, is first told to go to the red dot, green dot, and blue, but in a different task, it has to go to blue dot, red dot, and so on, right? And you can see like all kinds of robotic tasks would have this kind of compositionality. You have to first kind of go reach, you have to kind of go to the object, try to grasp it, lift it. So there is inherent compositionality in so many tasks. And the question we asked was, can we infer what is this breakdown of tasks, right? What is the right mix of different tasks in the current task? If we can understand what the current task is, we can do much better. Again, here the key is unsupervised learning, right? So the constant theme throughout this talk is unsupervised learning. If we could understand what is the current task, then we can do much better. And that's what we designed in this algorithm that kind of combined both global context and local context and online adapted to changes in the tasks. And, I won't give the details, but here the algorithm, you can see, much more easily adapts to the change in the destination, right? So here I'm changing this destination online and it's quickly able to move there. Even this seemingly simple task, you can see, sorry, this kind of got changed. If you see the baseline here, right? So the baseline is not able to keep up, and that's the idea. It was only supposed to show the baseline. I don't know what happened here. So that's the idea that, if we can do accurate task inference, then we can adapt and we can quickly change tasks and still be able to handle and do well. Yeah, so I want to now conclude the talk and say that to create generalizable AI, we need rethinking of deep learning, right? So we shouldn't go with just the standard paradigm of saying we have label data, let's build a reasonable architecture, let's train it with a standard loss function, and we are done. I think the key is unsupervised learning, and we cannot get around that problem. Unsupervised learning can be hard, but there are so many ways that we can make this tractable. And looking at inspirations from our own brain has been very productive, because we can build this recurrent feedback and incorporate generative modeling with unsupervised learning to enhance robustness. Then we can incorporate ideas from symbolic AI and do hybrid neurosymbolic AI that gives us compositionality, but also the ability to learn from data, both symbolic data as well as numerical data. And then we can extrapolate to entirely new, harder examples than what's been seen during training. And then finally, I think the role of robust priors is so critical. And in many scientific domains, there is such rich knowledge that can give us these priors. And incorporating them and blending them with machine learning in the right way is crucial for us to get gains that is very domain specific. And currently, we don't have a universal or an automated way to do this. It's working closely with domain experts that's making it possible. But hopefully, we'll find AutoML that could try to find this right blend of prior knowledge and data-driven methods together. And finally, I gave some brief ideas in terms of how to enhance our unsupervised learning methods, how to have trustworthy AI with better confidence levels, how to design for adaptive AI that can learn new tasks very quickly, that can understand how a task breaks down into subtasks and be able to adapt very quickly. I think all these ingredients are crucial for generalizable AI. Thank you.
Excellent. Thank you, Anima. Thanks for this wonderful presentation. And so number one is a little bit more of a general question, really, around comments on, deep learning on graph data and what the biggest challenges are.
Thank you. So I can see the question now. You're saying the current status of deep learning on graphs, right? What is the biggest challenge? So for graphs, the aspect is, again, right, in domains such as the molecules that I showed, the graph is natural because we know the graph in terms of how the molecule is organized. So it's not just the graphs, but also what kind of features to learn on graphs, right? So, and in case of chemistry, we know these molecular orbital features create already a good invariance, right? So we don't have to worry about all the transformations that are the same. And if we have to learn this from data itself, that's much harder. And I think that's the challenge in other domains where we don't have such features already built because of domain knowledge. Because if you look at all possible
maybe just one question related to ethics. I know we had to get there, right? To what degree will the emergence and increasing sophistication of unsupervised AI make government surveillance and control over citizens more effective? Hopefully you can give us some general comments on that.
Sure. I think ultimately, right, with any technology, there's both beneficial and bad uses of technology. So I think I'm hopeful that humanity will figure out, indeed, with increasingly sophisticated algorithms, right, there is potential for more misuse and more also authoritarian regimes using it to surveil on the citizens. But at the same time, when AI is democratized and we are publishing so much openly and the code bases are available, and if we can also create data sets that are, available to researchers, but also tightly controlled, right? We still haven't figured out what that mechanism is. My hope is it's not just then the power in the hands of a few. So the best way is to openly talk about this, right? Like talks like this, which are great for enhancing the knowledge of the public and democratizing AI. I think that's the solution.
Okay, great. And maybe moving to some technical questions, mostly around CNN feedback. There seems to be the general question, do you have a good reference for the CNNs with feedback?
Certainly. We have a paper that's now on archive. I'm happy to send that over, and maybe you can add it in the link. But it's also searchable if you search my name and the feedback that should come up.
Yeah, and then related to that, do you have some comments around the difference between the general GAN architectures? And, how do you look at the different network types? Are they different? Are they maybe similar?
That's right. So I think like philosophically, the GAN architecture is focused mostly on the realistic generation. In fact, that's the feedback given to the discriminator there, right? Whereas here we are focusing ultimately on good classification and the generation as a way to check for consistency. And, in the results I showed, we, for the more complex data sets, we are not even going up to the image level, right? We are not going to generate the actual image, but some intermediate features for the feedback loop. And the idea is if we kind of now have a good idea of what the intermediate features of a cat look like, right, then we can enhance and work in that feedback loop. And that's what the brain does anyway, right? So sometimes, of course, we can hallucinate and see an actual cat in our brain, but most of the time we don't, right? It's implicitly there, some representation of the cat, and we know it's a cat. And so we don't have to actually visualize the image in the feedback loop. That's the short answer. Okay.
Excellent. And there's quite a few more questions. I'm afraid, unfortunately, we have run out of time today. I apologize again for some of the technical difficulties that we have, but you will get the video recording afterwards where we will be able to clean that all up. I'd like to thank Anima again for her very informative presentation, her insightful answers to the many questions. And a special thanks to each one of you here for taking the time to attend, to participate, and to stick with us throughout the technical hiccups. This talk was recorded and will be available online in a few days at learning.acm.org. You can also find announcements on upcoming talks and other ACM activities at acm.org. And please don't forget to fill out our quick survey. You can suggest future topics or speakers, which you should see now on your screen as well. So again, on behalf of ACM, on behalf of Anima Anandkumar and myself, Michael Zeller, thanks again for joining us today. I hope you will join us again in the future. And this concludes today's webinar. Thank you.
Thank you. Thanks a lot for having me. And I'm easily, I'm on social media. So if you have any questions, feel free to reach out there. Thanks a lot.